Everything looks in order. It's gonna work. It has to work. I hope you're right. Okay, bring up the monitors. She looks stable. Wait a minute. Oh. First, you're gonna have to learn what kind of wormholes there are.
The wormhole spectrum is one that we split into two parts, Lorentzian and Euclidean varieties. It is the metric signature that separates these metrics. Lorentzian manifolds being of a pseudo-Riemannian type, and the Euclidean being of pure Riemannian type. Experimental physics seems to take place in Lorentzian signature, therefore our focus will reside here. Given a loose definition, a wormhole is an compact region of spacetime with a topological simple boundary, but a topological non-trivial interior. Lorentzian wormholes can be categorized into two classes: permanent and transient wormholes, each of which has its own intro-universe and inter-universe subspecies depending on whether or not the wormhole connects distant regions of one universe to itself, or connects different universes in the so-called multiverse. Further categorization arises when one considers microscopic and macroscopic varieties. If one slices spacetime into space-like hypersurfaces, and each slice of space is considered a three-dimensional Riemannian manifold, then if a wormhole exists it can be thought of as existing throughout a certain duration or interval of time.
Recall that a space-like hypersurface is a slice of space-time that represents a single moment in time across all space. That is, that every pair of nearby points is separated by a space-like interval. That is, no causal signals, like light or matter, can travel between them. More precisely, in a 3 plus 1 dimensional Lorentzian manifold, our spacetime, a hypersurface, capital sigma, is called spacelike if the induced metric on it is Riemannian, which means that it only has positive eigenvalues, no time direction. This means that the normal vector, n mu, to the hypersurface is timelike, and therefore the metric squared with the normal vector is less than 0. So if you imagine a surface cut through space-time, such that all observers on the surface would consider it to be the same instant, though they may disagree on what time it is, then you're looking at a space-like hypersurface. Why it matters in general relativity. Space-like hypersurfaces are often used in initial value formalisms of Einstein's equations. The ADM formalism breaks space-time into a stack of space-like hypersurfaces labeled by time. This is crucial for numerical relativity and analyzing gravitational dynamics. Under this formalism, space-time manifold M is foliated into a family of space-like hypersurfaces sigma sub t, each surface being labeled by a time parameter t, so that the manifold M is the union of all such space-like hypersurfaces. The 3 plus 1 decomposition of the metric is written as ds squared equals negative alpha squared dt squared plus gamma ij, multiplied with dxi plus beta I dt and dxj plus beta j dt as well, where one can call alpha the lapse function, telling how time progresses from one hypersurface to the next, beta I shift function in a sideways manner, and gamma ij is the induced 3 metric on the hypersurface sigma t. And the hypersurface constraints on the Einstein equations will split into the following: Hamiltonian constraint and momentum constraint. Quasi-permanent wormholes are the type that are essentially three-dimensional objects that exist in a finite time. The existence of truly permanent wormholes, as opposed to quasi-permanent wormholes, does not violate any of the classical topology change theorems. However, the creation and the destruction of quasi-permanent wormholes violates the classical topology change theorems and requires either some mutilation of my classical general relativity or fall on the less understood realm of quantum gravity. A more formal definition. If a Lorentzian spacetime contains a compact region, omega, and if the topology of omega is of the form R cross sigma, where sigma is a 3-manifold of non-trivial topology, whose boundary is approximately S2, and if furthermore the hypersurfaces sigma are all space-like, then the region omega contains a quasi-permanent intra-universe wormhole. A wormhole connecting different regions of our own universe. Any compact region, omega, with a boundary approximately to S3, that contains a non-trivial topology is certainly an intra-universe transient wormhole. And by hypothesis, the topology of omega is certainly not of the form r cross sigma. Transient inter-universe wormholes typically have an active region with topology approximately r cross S3, the boundary being given as S3 in union with S3. Thus, a required mutilation of the classical general relativity is necessary for classical topological changes. Macroscopic versus microscopic wormholes. There exists a somewhat crude division into macroscopic and microscopic wormholes, depending on the size of the active region in comparison to the Planck length. Wheeler wormholes, deriving their existence from the assumed vacuum fluctuations, take place in spacetime quantum foam. Those are definitely microscopic in nature. They are typically transient, though, by sheer luck, may arise within the topology suitable to be considered quasi-permanent. The taxonomy of Wheeler wormholes depends critically on one's input assumptions as to what it means to quantize gravity. Traversable wormholes. A Lorentzian wormhole that is quasi-permanent and macroscopic might be suitable for travel by humans. Euclidean wormholes are typically transient and are commonly thought of as instantons in the gravitational field. If one adopts a canonical or a path integral quantization formalism, then one is forced to conclude that only through promiscuous attitude toward manifolds would one find themselves in a cold universe, devoid of any activity most of the time. We do not live in such a universe. Would-be wormholes containing event horizons, as in the Einstein-Rosen bridge, or non-traversable Schwarzschild wormholes, are bad news due to the event horizon. Observers watching someone enter will have to wait an awfully long time to hear news from the exit. What's worse, hiding behind event horizons are nasty fatal objects. Inner horizons, typically unstable, lead to very cooked travelers and tidal forces large enough to rip an intrepid explorer to bloody shreds. Yes, well, Wheeler wormholes, being of microscopic order, are of the size 10 to the negative 35 meters, the Planck length, and unless some new physics allows us to scale these processes to macroscopic sizes, they are of no use to us. In fact, wormholes based on naked singularities, such as the Kerr wormhole, are badly diseased for all the standard reasons of naked singularities themselves, namely the cosmic censorship theorem and tidal forces. It was Roger Penrose who insisted that nature abhors a naked singularity, proposing the preservation of determinism in Einstein's equations. And this is not a theory, but for now remains a conjecture. Morris and Thorne realized that the analysis is radically simplified if one adopts a more engineering approach to the idea. Assuming the existence of a suitable, well-behaved, interesting geometry, calculate the Riemann tensor associated with this geometry, and use the Einstein field equations to deduce what the distribution of the stress-energy tensor must be. More technically, we shall see that matter near the throat violates the so-called null energy condition, the NEC. Roughly speaking, somewhere near the throat of the wormhole, one encounters a negative energy density. However, we do know that some quantum effects do lead to small, measurable, experimentally verified violations of the NEC, such as the Casimir effect. If it were not for this, the work of Morris and Thorne would be interpreted as the beginning stages of a no wormhole theorem. The metric. To keep the analysis tractable, Morris and Thorne assumed that their traversable wormholes were time-independent, non-rotating, and spherically symmetric bridges between two universes. The manifold of interest is thus a static, spherically symmetric spacetime possessing two asymptotically flat regions. Next, we let L denote the proper radial distance, that is, the actual physical distance as measured by a ruler or an observer that is moving radially. That would be the distance measured in the curved spacetime. And so we note, dl is given by the square root of the GRR component multiplied by dr. So to compute L, the proper radial distance, all we need to do is integrate this term from R1 to R2. Then, without loss of generality, the spacetime metric can be put in the following form. ds squared is equal to negative e raised to the 2 phi of L dt squared plus dl squared plus r squared multiplied by d theta plus sine squared d phi squared, and L taking on all real values. The assumed absence of an event horizon implies that phi of L, the redshift function, must be finite everywhere, the two asymptotically flat regions occurring as L goes to plus or minus infinity. In order for the spatial geometry to tend to an appropriate asymptotically flat limit, one must impose that the limit as L goes to plus or minus infinity of R over the absolute value of L must go to 1. We also require that the redshift function as L goes to positive or negative infinity is finite. The radius of the wormhole throat is defined by r sub 0, which is the minimum value for r of L, and for simplicity, one may assume that there is only one such minimum, that is, an isolated minimum. And of course, without loss of generality, we can take the throat to occur at L equals 0. The metric components should be at least twice differentiable as functions of L. And these would be the minimum requirements to obtain a wormhole that is, in theory, traversable. For further simplicity, one might assume symmetry under the interchange of the two asymptotically flat regions, making L go to negative L, that is. And thus we have R of L is equal to R of negative L, as well as phi of L is equal to phi of negative L. This is not an essential requirement, but certainly reduces the complexity of our calculations. Now, one can use these symmetries to calculate the Riemann, the Ricci, and the Einstein tensors using this coordinate system. The results are somewhat unwieldy. So it turns out to be more efficient to adopt the Schwarzschild coordinates and reparameterize the functional dependence of the metric in order to obtain a somewhat simpler expression. In Schwarzschild coordinates, tr, theta, and phi, we have ds squared given by this form of the metric, where the time dependence is captured by the redshift function. And two coordinate patches are now required, each one covering the range from the minimum r sub 0 to infinity. And these two patches are joined at the throat of the wormhole at r sub 0. Unpacking the Morris-Thorne metric. The Morris-Thorne metric given here incorporates two new functions. The redshift function phi of r, which controls the time dilation effects. And if phi of r is finite everywhere, then there is no event horizon, i.e., the wormhole is traversable. The other function that we look at in the Morris-Thorne metric is the shape function. B of r is the shape function that determines the wormhole's, spatial shape. In other words, it controls the geometry in the space-like slices. The wormhole will flare out if the derivative at the throat is less than 1. And where r is equal to the throat, b of r is equal to r sub 0. If the shape is greater than r, then space-time would be pinching in and thus not be traversable. Now for convenience, we shall demand that the time coordinate t be continuous across the throat so that our redshift function on either end of the entrance and the exit will have that time flows at the same rate on both ends. The two arbitrary functions phi of L and r of L have been traded in now for the four arbitrary functions plus or minus phi and plus or minus b. The radius of the spherical shells surrounding the traversable wormhole versus the proper radial distance from the throat can be analyzed graphically so that one can see the wormhole is non-zero at the throat. The proper radial distance L is related to the coordinate r in the following way. One requires both limits to be finite. In the case of the limit as r goes to infinity, our shape function must take on a finite value on either end of the wormhole. By comparison with the Schwarzschild metric, this implies that the mass of the wormhole, as seen from spatial infinity, is given by b plus or minus equal to 2gm plus or minus, where m plus or minus represents the mass of the wormhole on either side. And note that the mass of the wormhole is allowed to be different depending on which universe the observer resides. That is, the two mounds can have different masses. We would also require that the limit as r goes to infinity of our redshift function be finite, again going to plus or minus phi, and the non-a priori requirement that at spatial infinity these functions be seen as equal implies that time can run at different rates in the two universes. Since dr by dl is equal to 0 at the throat of the wormhole, we must have dl dr go to infinity as well. What this implies is that our shape function at the throat is equal to r sub 0, and away from the throat of the wormhole, the shape function is less than r. Away from the throat, the metric component should be at least twice differentiable functions of r. And for simplicity, one must assume symmetry under the interchange of the asymptotically flat regions. That is, the shape function must be the same on either end of the wormhole, and the redshift function be the same on either end of the wormhole. This requirement is again not essential, but very useful when we employ symmetry. One notices that dr by dl is equal to plus or minus the root of 1 minus b over r, which yields a second derivative here of 1/2 dr multiplied by dr dl squared, and that gives us the result 1 over 2r multiplied by b over r minus b prime, primes denoting derivatives with respect to the variable r. Since r of L is a minimum at the throat, and grows as one moves away from the throat, one deduces that there exists some radius, r star, that for all radii within the throat range to that radius, the second derivative is positive, from which we conclude that there exists a radius r star for all radii in this interval for which the shape function's prime, b prime, is less than b over r. At the throat itself, where b of r is equal to r0, we can evaluate the second derivative at r sub 0 and get the following expressions, again employing the symmetry that these things are equal at either end of the throat. And that implies that their derivatives are equal at either end of the throat as well. Moreover, r of L is a minimum at the throat, and also, as one knows, dr dl evaluated at the throat being greater than or equal to 0, whence one obtains this weak inequality that b prime plus or minus at the throat is less than or equal to 1. Now, since we know that the shape function goes to 2gm as r goes to infinity, and that the shape function is less than r away from the throat, we recall that the throat is the first and only place where the shape function is equal to the radius of the throat. And since the shape function goes to a finite limit as r goes to infinity, the outermost crossing of the line b equals r must occur at a slope that is less than or equal to 1, indicated by the graph above. Similar considerations apply to the redshift function. We note that the derivative of the redshift function with respect to L is given by the root of 1 minus b over r multiplied by phi prime. And that will help us calculate the second derivative with respect to L of the redshift function, and we get this expression involving phi prime and phi double prime. Again, evaluating this at the throat, at r sub 0, we obtain the following values. And again, by symmetry, this implies that the rate of change of the redshift function on either end of the wormhole mouths are equal. Again, not an essential, but helpful property. Curvature considerations. Brute force computation of the Riemann, Ricci, and Einstein tensors is readily carried out. For the time being, we will suppress the plus or minus subscripts which differentiate the universe in which each of the mouths reside, respectively. Here are the results in an orthonormal basis. The first of the Riemann tensor components is given by this expression. This term encodes the tidal acceleration in the radial direction due to space-time curvature. Radial tidal forces are the differential gravitational forces experienced by different parts of an object along the radial, inward or outward directions in a gravitational field. They arise because gravity is stronger the closer you are to the mass generating the field. That is, it measures how a radial separation between two nearby free-falling observers affect the relative acceleration in the time direction. When this component of the Riemann curvature tensor is positive, it creates tidal stretching. When negative, tidal pinching or compression. Considering the non-zero components of the Riemann curvature tensor, here the time components are given by this expression. This represents the tidal effects in the theta and phi directions respectively, that are the azimuthal and polar directions. When we look at these non-zero components of the Riemann curvature tensor, with the radial component being compared to the angular components, we see that this describes how spatial geometry bends in the radial and the angular direction specifically, how small angular separations behave as you move radially, outward or inward. And then when one compares the Riemann curvature tensor of the different angular components to themselves, we do get this non-zero expression, capturing the spatial curvature in the angular sector of space-time if we consider the two-sphere formed by the angular components theta and phi and create a volumic sector. Then that's what this is capturing. It captures the spatial curvature in this angular sector. This term directly connects to the angular tidal forces and the intrinsic geometry of the spherical surface. All other Riemann components vanish, that is, they go to zero. So calculating the non-zero components of the Einstein tensor, we get the following results. This represents the energy density measured by a local static observer at the point in space-time. This component of the Einstein tensor gives us this expression here, and this is the radial pressure, that is, the pressure along the radial direction, as measured by a static local observer at that point in space-time. The two angular components of the Einstein tensor are given by this expression, and this expression represents the transverse pressures experienced in the theta and phi angular directions. One now evaluates these particular expressions at the throat of the wormhole, that is, at r sub 0, and we get the following expressions. One can see that the derivatives of both the shape function and the redshift function show up in some of these expressions. Now one notes, because of continuity conditions applying to b prime and phi prime at the throat, we do not have to distinguish between the b plus or minus or the phi plus or minus in the formula above. That is, the subscripts won't really matter due to the symmetry. The analogous Einstein tensor results at the throat are given here, and due to spherical symmetry, the two angular components are equal. And this allows us to deduce the energy conditions. Finally, we examine the Einstein field equations in order to extract the stress-energy components And so we let the non-zero components of the stress energy tensor be given by the following new variables. Rho, which is the energy density in the time component, the radial tension minus the radial pressure being given by negative tau, and the transverse pressures being given by lowercase p. The Einstein equations for general relativity, given here g mu nu equals 8 pi g t mu nu, now yield the following system of equations in terms of these new variables, the energy density, tau, and p, our pressure. So now, what we do is a convenient rearrangement will allow us to rewrite some of these formulae. And we can write the functions b prime, phi prime, and tau prime in terms of these coordinates. The first of these can be easily integrated to yield the following shape function. And that gives us 2gmr, which is a new mass function which we can represent here. And we can give this as the effective mass inside the radius r. The shape function thus has a very direct interpretation in terms of the distribution of mass inside the wormhole. And as one moves to spatial infinity, that is letting r go to infinity, this mass function obtains the value of capital M, the total mass of the wormhole. At the throat itself, the energy density is given by this expression, the new radial component tau, and the pressure P. So, evaluating these things at the throat tells us that the mass function satisfies the following conditions. There exists an R star, for which all radii from the throat to r star gives us an energy density less than mr over 4 pi r cubed. And then at the throat itself, it's less than 1 over 8 pi gr sub 0 squared. And the two equations that we just looked at, the first two of those can be combined to give this following expression. Now, since we know that this particular term evaluated that the throat must go to 0, while for all r greater than the throat size radii, we have this expression being greater than 0, we therefore have an existence of a radii r star tilde, for which this expression's derivative is greater than 0, with r star tilde typically near the throat of the wormhole. And from this, one readily deduces that there exists an r star tilde that for all radii within the range of the throat to this radius, the energy density minus tau is always less than 0. Working at the throat itself, this results in the weak inequality that says the following, which interprets as a negative energy density at the throat. for simplicity, the entire discussion has been phrased in terms of an inter-universe wormhole. That is, in two distinct asymptotically flat spacetimes, two different universes. However, since both mouths reside in these regions of spacetime, one can, with minimal distortion, rearrange the mouths to reside in one asymptotically flat region. That is, both mouths would exist in our universe. We would say that this would produce an intra-universe wormhole, which is traversable. These wormholes lead to some additional levels of complication, however. You see, if time runs at different rates in the two universes of the inter-universe wormhole, then the associated intra-universe wormhole has a non-conservative gravitational field. Also, non-orientable spacetimes, although acceptable at the classical level, present problems at the quantum level. Further curvature considerations. One can use the mass function together with the field equations to obtain some interesting results. It allows one to rewrite formulas for the Riemann tensor as a function of rho, tau, and p, as well as the mass function m of r, as well as r itself. And in that orthonormal basis, we get the following results. One sees, though, that with this rearrangement of the Riemann tensor, we have eliminated the redshift function phi of r in terms of locally measured quantities, and a global piece, which is the mass, m of r. Of course, we evaluate these quantities at the throat, and one can express the Riemann tensor in terms of the stress-energy tensor. And these results let us get a grasp on what the energy conditions for our wormhole will be. The imprint at infinity. In any asymptotically flat spacetime, it is possible to define the so-called imprint at infinity. This observation is the basis for the derivation of asymptotic conservation laws. ADM mass. The ADM mass is the total mass energy as seen from infinity. It's an important assumption for the asymptotically flat spacetimes like wormholes. And for a wormhole to be viable, the ADM mass must be finite. You can think of this as the mass as viewed from very far away. In a wormhole spacetime, this affects gravitational influence on distant objects. You see, if the ADM mass is negative, then the wormhole is repulsive at infinity. Strange. Positive ADM mass behaves more like a massive object from far away. That is what we would expect a wormhole to look like. But looks can be deceiving. and sufficiently far into the asymptotically flat region, one can adopt a quasi-Minkowski's coordinate system, in which the active region is assumed to be confined to a small radius r. Then the metric can be expanded to to first order, and the total ADM mass is defined by the suitable normalization of the coefficients of the 1 over r term in this expansion. As we consider our formalism further, the ADM mass can also be more formally defined in terms of a suitable limit of surface integrals at spatial infinity. If we let omega be a spacelike 2 surface enclosing the active region, then integrating over this surface will give us m is equal to 1 over 16 pi g times the limit as this region goes to infinity of the following integral, where ni is the unit outward normal. The important feature of the ADM mass is that it is conserved. Analyzing what matters. Considering the case of a traversable wormhole that connects two otherwise separate universes, there would then be two ADM masses at either mouth of the wormhole, at the plus and the minus end, which in general do not have to be equal. The conservation law normally deduced from the ADM mass carries through to a pair of conservation laws. Each mass, m positive and m minus, is conserved separately. Consider a test mass m that is initially far away from the wormhole mouth, let's say in the plus universe. Suppose now that this object traverses the wormhole and eventually settles down far away from the exiting mouth in the minus universe. Then we consider the imprint at infinity. The total ADM masses on both sides of the wormhole satisfy the following equations. In the plus universe, the total mass is given by the initial mass of the wormhole plus the test initial mass, and that's going to equal the final mass in the positive universe, and one can follow a similar reasoning for what happens in the exiting universe. When massive objects traverse the wormhole, they alter the mass of the mouth that they pass through. And for generality, we can allow for the fact that the initial and final mass are not equal. This allows for the possibility that the objects traversing the wormhole may gain or lose some kinetic energy in the process. Now, so what about those intra-universe wormholes that we are really interested in? You know, the ones that can transport us from different regions of our own universe. Well, provided that the two mouths are sufficiently far apart that their mutual gravitational attraction is negligible, and that the initial and final positions of the object traversing the wormhole are sufficiently far away from both mouths, then what can we deduce? What can we say about these intra-universe wormholes? Well, the total ADM mass for the one universe is then given to be m total is the total wormhole mouths on either end plus the initial mass going in, and that would equal the total mass of both mouths on either side in the final state plus the final mass exiting. Because of the assumed negligible gravitational interaction, we can still assert these two conditions, and that suggests that, but does not prove, the possibility of a fundamental limit on the total mass that can traverse the wormhole. In other words, perhaps there is a limit to how big an object can actually go through. For a sufficiently large transfer of mass, the final mass of the emitting wormhole mouth becomes negative. And under normal circumstances, this would be considered a complete disaster. However, we shall see that when examining the energy conditions, specifically the null energy condition, or the NEC, that it is a violation of the average null energy condition, which is required in order to hold the mouth of the wormhole open in the first place. It is because of this reason that the hypothesis used to derive the usual version of the positive mass theorem do not apply to traversable wormholes. There is no guarantee apparent that would prevent a total mass of a wormhole from going completely negative. Although such behavior would certainly make one feel rather queasy. If the emitting mouth of the wormhole becomes negative, one has the possibility of a runaway reaction. That is, its mass now being negative, the emitting mouth will now gravitationally repel the ambient medium. The absorbing mouth will continue to lose mass, and its mass will become more and more negative, thereby reinforcing its repulsion of the ambient medium. So in order to hold a wormhole open, you need matter that violates the usual energy conditions of general relativity. The key energy conditions imposed by the stress energy tensor T mu nu are as follows. We have our null energy condition for any null vector k mu. This is the condition that says light rays see non-negative energy. The weak energy condition is for all time-like vectors, u mu. Measured energy density is non-negative. The strong energy condition would be that the stress energy tensor would satisfy this condition, which is a way of saying that gravity is always attractive. And there's the dominant energy condition, which states this, where the following quantity is not space-like, and that's a statement that says energy flows at or below the speed of light. But in order to really satisfy, or at least look at the important conditions, it's the null energy condition we really care about. For traversable wormholes, the null energy condition is the most relevant, and in order to hold that wormhole open, we must violate it. The NEC violation appears then as this statement, where we have the reverse inequality for radial null vectors, that is, light vectors. These correspond with the conditions that the energy density plus the pressure in the radial condition is negative, and the energy density and the radial pressure are given by the stress energy tensor components. So at or near the throat of the wormhole, the stress energy tensor must be satisfied. The negative energy density, or the tension stronger than the energy density, creates a kind of matter called exotic matter, where one assumes the stress energy tensor of the type given here. The energy density and the principal pressures being given along the main diagonal. For completion, one would ask, how does one violate the energy conditions? What is the catalyst that brings forth the spark, igniting the traversable wormhole into existence? Well, this answer lies in understanding what and if exotic matter is possible. Matter that has a negative energy density. Matter that creates repulsive gravity. What some people might mistake as anti-gravity. One could speculate that if exotic quantum effects could stabilize a captured wormhole that's flickering in and out of the quantum foam, then one could find a way to inflate them into the macroscopic world. And although this sounds a lot like science fiction, it was Albert Einstein who said, "Imagination is more important than knowledge." Suffice it to say, even if we could engineer wormholes to distant parts of the known universe, it would still take over 1 billion human lifetimes to find out what's even remotely out there. And by that time, we may no longer be human. That relativity, man. They get older, I stay the same age.